Hello, and I would like to show some intuition about electric circuits that are arranged with resistors in series and then also arranged with resistors in parallel. Notice that I will start with the simplest cases we could think of and simple observations, and then I will add greater amounts of complexity. And let us assume that we can be more quantitative as time goes along in this video and add greater levels of mathematical detail and sophistication. So what we have here is a 100-volt battery with a switch that can be toggled off or on. So the switch is in the open position right now. There is 0 amperes of current and 0 watts of power dissipated. If I close the switch, notice that the bulb will burn at a certain brightness. That's because 100 volts and 100 ohms, this will be 100 squared divided by R. That'll give us the power. So that's going to be 10 to the 2 squared, that's 10 to the 4th, divided by 10 to the 2, you'll just get 10 to the 2, and that's 100. That's 100 watts. So this is a 100 watt bulb. Fine, this is what we see right there. And then 1 ampere for current, 100 volts divided by 100 ohms for 1 ampere. Let's open the switch, but now let's add a second bulb. And remember, this is sort of rated, if you will, as a 100 watt bulb. But notice when we close the switch, you'll see that we only have half an ampere and 25 watts. Also notice that each bulb is 25 watts, but together they add to 50 watts. Let's think about what's going on. First of all, the voltage that's being delivered by the battery is the same voltage across the entire circuit. Secondly, notice that the bulbs look dimmer because each is only 25 watts. The entire resistance now is 200 ohms. 100 volts divided by 200 ohms gives us 0.5 amperes for the current in the circuit. But then notice that each bulb is only a quarter as bright as the original 100 watt bulb. That's because the current is half, but also the voltage across each bulb is half. Okay? And then notice that progressively, as we add more bulbs, the current continues to go down, and then the power in each bulb continues to go down, and in fact the brightness of each bulb goes down further and further. Note now we have a simple setup of a parallel circuit. As before, there's a 100 volt battery, 100 ohm resistance, and we can close a switch. So when we do that at first, we get a 100 watt light bulb to glow. That's because this is meant to be 100 volts. Fine, that gives us 1 ampere. Now if we open the switch and add a second bulb, notice there's going to be multiple paths for the current to move on. Notice that the electrical resistance is actually going to be less for the entire circuit compared to a single bulb, because there's many paths for the current to move on. Notice the geometry of parallel is like the rungs of a ladder, where each branch has a separate path for the current to flow, and when we close the switch, we'll see that the power of each bulb will remain 100 watts. So that means the power of the entire circuit will be 200 watts, but notice that the current now goes up to 2 amperes. Why is that? Well, the only way to get 2 amperes current coming out of or back into the battery is to take 100 volts and divide by a half of an ohm. Divide by 50 ohms. How do we get 50 ohms? Well, it turns out we use the so-called reciprocal rule for resistors, where we do 1 over 100 plus 1 over 100, and we add them and then take the reciprocal at the end. So that's 2 over 100, reciprocal is 100 over 2, or 50 ohms. So two resistors in parallel, given that there's two paths for the current to flow, is actually half of each bulb's resistance. If I open the switch and then add a third bulb, there should be 3 paths for the current to flow on. There should be 1 ampere of current in each bulb. Why? Because the voltage difference across each branch should be 100 volts, because the left-hand side of each of these should be connected to the positive terminal of the battery, whereas the right-hand side of each of these bulbs is connected to the negative terminal of the battery. So each will contribute 1.0 amperes. When we get back to the battery will be putting out 3.0 amperes. Notice each bulb will glow just as bright as it was if it was a single bulb, and that's because each is going to be 100 watts of brightness, and this is hopefully what you observe. So note that our homes are hooked up in parallel because each a device is going to act independently, even though some could be on the same overall breaker circuit in home installation. Now let us pick up with a more quantitative, slightly more realistic version simulation of a series circuit. Notice what we have changed is now the battery voltage is 12 volts, and notice that the resistance of each of the bulbs is 6.0 ohms. Okay? We can control the battery voltage and the resistance of each of the bulbs. Here we have an ammeter to measure the electric current through the circuit, the series circuit. We have a switch we can close or open. Right now the switch is open. And then we'll also use a voltmeter here in just a moment to measure voltages across the battery and then also across these bulbs. So let's flip the switch and let's see how that looks compared to another similar video I did a while ago, and compare the bulb brightness to a brightness of a single 6.0 ohm bulb. And you'll notice that these bulbs are each pretty dim, and that's because the total resistance is 12 ohms. That's 6 ohms plus 6 ohms. So when resistors are in series, the overall resistance adds 12 ohms for the total resistance and 12 volts for the total voltage. 12 volts divided by 12 ohms gives 1.0 amperes by Ohm's law. Also notice that the bulbs here are, I think, 1/4 as bright as a single 6 ohm bulb. If you don't believe me, let me go ahead and open the switch here, take this bulb out for just a moment, reconnect the circuit, and you can hopefully see that this bulb is quite a bit brighter. Also notice that the current is twice as much because now it's 12 volts divided by 6 ohms, and the charges move faster. Okay, in fact, twice as fast. So let us put this bulb back in. Okay, so I'll insert this into the circuit in series. Okay, fine. Now these two bulbs should be the same brightness as each other, but notice that they're 1/4 as bright. Let's think about why that is. That's because the current is half as much as the single 6 ohm resistor case, but also the voltage drop across a single 6 ohm resistor had to be 12 volts. But the voltage drop, that is the energy per charge used in each of these bulbs, is going to be 6 volts because it's going to be half the energy dissipated from the battery. Notice again, it's 0 volts on a single piece of wire, but that's just wire. But then across this bulb, it's 6 volts. It's going to be 12 volts change across both the bulbs. Okay. Now let's make a little change, everyone. Let's now see how things look different if we have unequal resistors. So if we have two resistors that are of different resistance rating, let's see what the result is. So let's open the switch, and let's make one of these resistors twice as much resistance as before. So let's change this to 12 ohms. Now let's think through carefully. What's the total resistance going to be? It's going to be 18 ohms. I ask you when I pause to pause the video and think about it before you just hear me give the answer. 12 volts divided by 18 ohms should be 2/3, so 2/3 of an ampere. So I think the current here will read 0.66 or 0.67 depending upon how it rounds. Now let's think about the voltage drop. The voltage drop across this resistor versus this resistor, I think the current is going to be the same everywhere in the series circuit because the current has to go through all the devices. But also, furthermore, even if the current is the same and it's 2/3 of an ampere, 2/3 of an ampere times 6, that's going to be 12/3. So that's 4. That's 4 volts. Energy drop by V equals IR across the first resistor. But across the second resistor, that's going to be 2/3 times 12. So that's 24/3, which is 8. That's going to be 8 volts. But wait, 4 volts plus 8 volts is going to give 12 volts because that's the voltage of the battery. So notice that if you have twice as much resistance, you should have twice as much voltage dissipated in the resistor as long as the current is the same for all devices, namely that's a series circuit. So let's go ahead and see what this looks like. Okay, so let's see what happens when we close the switch. Notice that the bulbs are indeed dimmer, that the 6 ohm resistor and the 12 ohm resistor only produce 2/3 of an ampere. Notice the current is moving quite slow, but also notice the bulbs are dimmer than last time, but notice the 12.0 ohm resistor is twice as bright as the 6.0 ohm resistor. Why? By the equation I squared times R equals power. I, the current, is the same, but the resistance is twice as much, so the brightness is twice as much. But also we said that this should dissipate twice as much voltage. Let's see if we can verify that. So the voltage change across the 6 ohm resistor is indeed 4.0 volts. But notice the voltage across this middle line is 0 volts because that's no difference in potential. And the voltage difference across this second bulb is indeed 8.0 volts. And that's because it has twice as much resistance, twice as much power dissipated, thus also twice as much electric potential energy per unit charge, twice as much voltage. Let's make one more change. Now, let's go back to 3 resistors. Okay, so 3 resistors. I'll open the switch. Let's have them all be 6 ohms. So let's snip here. So I think they all should be the same brightness. Okay, so I'll just move this down so you can see it a little better. And I think that 18 ohms is going to be the same resistance we had just a moment ago. So when we close the switch, these all should be the same brightness. But notice that, again, we have 2/3 of an ampere. But notice this is 12 volts and then there's 3 equal resistors. I think they should each dissipate now 4 volts. So let's take a look. Yes, 4 volts. Notice 2 of them is 8 volts, and any single one of them should be 4 volts. 3 equal sized resistors, 4 volts dissipated for each resistor. Now, what if it's a little more complicated? What if I open the switch And now let's have the third resistor. Let's call this 1, 2, and 3. Let's have the third resistor stay 6 ohms. Let's have this become only 2 ohms. And let's have this become 1 ohm. Okay, so now first of all, I think the current's going to be a lot larger because the resistance has gone down. So 6 plus 2 plus 1 is 9. 12 divided by 9 is the same thing, I think, as 4 divided by 3. So that's 1.33 repeating, so 4/3 of an ampere. The voltage drop across this one should be I squared times R. So that's going to be 4 over 3 squared. That's going to be 9 over 4 times 1. So that's going to be 2.25 volts. And then this should be double. So that should be 5.5 volts. And then how about, let's see, 9 over 4 times 6. It'll be the remaining difference from 12 volts. So let's go ahead and flip the switch. Notice that this is twice as bright as this one, and this one is 3 times as bright as this other one. Okay, so that's the idea. Let's look at the current. It's 1.33 amperes like we predicted. The voltage across this device, the 1 ohm resistor, is 1.33 volts. Okay, so that's because, now before, sorry, when I was doing I squared times R, I was calculating the power. What I really wanted to calculate was the voltage. So it's current times resistance. Yes. So we should do 2.67 volts across this. That's because 4/3 times 2 is 8/3. And then finally, across this last resistor, we should have 8 volts, because that's 4/3 times 6, which is 24 over 3, so that's 8 volts. So hopefully that all makes sense. This is what we mean by a series circuit. Now, by the way, in a series circuit, if one device goes out, then all devices do, because they're all strung together in a single wire. Okay? In fact, this reminds me that if you've ever seen the wonderful movie National Lampoon's Christmas Vacation, not sure if I need to put a trademark or a copyright there, but as part of that movie, Chevy Chase is struggling getting his Christmas lights hooked up, or at least having them turned on. And his father says you have to check every single bulb and make sure that none of them are out, otherwise the whole string will be out. And it turns out that Chevy Chase had forgot to flip the switch to allow power to flow. His circuit was an open circuit, no longer not a closed circuit. But very old Christmas lights, circa 1980s or earlier, were hooked up in series. That is, if one bulb was out, the entire string was out. And notice that modern Christmas lights are not hooked up so much in series, but a little bit more in parallel. We'll talk about parallel in a moment, but nowadays, if a single light goes out, a small string of lights might go out, or if it's a very modern set, then only that single bulb will go out. Okay, so that's the idea for a series circuit. Now I'm going to show the quantitative intuition for a parallel circuit. Notice that I have several pieces to this parallel circuit. I have a 12-volt battery. I have 1, 2, 3 branches. In fact, let's call them branch 1, 2, and 3, resistor 1, 2, and 3, initially all set to 6 ohms, and an ammeter on each of the branches, and an ammeter that's going to go through the battery. So I did not install that, but I should in order for us to proceed. So let us have an ammeter installed here that reads the current that goes back into the battery. Okay, and then there are switches on next to the battery or on each of the branches. If we close the switch next to the battery, notice that there's going to be no current moving. That's because there's no path for the charge to move on a conductor. But let's go ahead and close the first switch on branch 1. It's relatively what we'd expect. Notice that charge flows from the negative terminal of the battery if we think about electrons. If we think about conventional current, positive charge would flow from the positive terminal of the battery to the positive side of the light bulb. Notice the current is 2.0 amperes, both out of the battery and through the light bulb. It looks like the brightness that we had in a single resistor circuit as we had before. Okay. Now let's make a little change. Let's open up the switch and let's open it up for both by the battery and branch number 1. But now let's close the switch for branch 1 and 2. So as soon as we close the switch next to the battery, no current moves, and then when we close it next to branch 1, we get 2.0 amperes. But now what do you think is going to happen when we close the switch for the second branch? Well, Ohm's law tells us that there should be current on the second branch because there's a path. And since there's more paths for the current to move, then the overall resistance of the circuit is going to go down. That is, the overall resistance is going to be given by the reciprocal rule, which will be 1 over 6 ohms plus 1 over 6 ohms. Add and then reciprocate. So that's 2 over 6. Reciprocal is 3. 3 ohms is going to be the resistance of these two resistors. Okay, so notice that. Furthermore, notice that there's going to be Ohm's law telling us that if the voltage across each branch is the same, which it has to be because each side, left side, is connected to the negative terminal of the battery, and each side over here of branch 1 and 2 is connected to the positive terminal of the battery, the 12 volts is the potential energy difference across each of these bulbs. Then we should have 2.0 amperes in each branch. But then, when we get back to the battery, we should have 4.0 amperes. That's because at this point where the electrons merge, call this a junction point, where they remerge to go back to the battery, or they split up at this junction point, you'll see that every electron we send up, we send another one to the right. So let's go ahead and hook this up. Close switch 1, close switch 2. First of all, notice that there's 2.0 amperes of current in each of the branches. Secondly, also notice that there is equal brightness between each of the two bulbs. Third, notice that at the junction point, electrons combine to now produce 4 amperes of current through the battery, and 4 amperes comes out of the battery and then splits up into 2.0 amperes and 2.0 amperes on each of these branches. Okay, so this is a junction point, but it's junction in terms of splitting up charge. This is a junction point in terms of merging charge. Okay, now let's close switch number 3. I hope you know what's going to happen. 2.0 amperes more, same brightness, but now the battery is going to really start to work hard. The battery is going to have 6 amperes coming out of it. And that means the battery is delivering a lot of charge per unit time, large current. So if this was a real battery that loses voltage over time, it would wear down pretty fast. So let's close this switch. Okay. So notice that the current across this battery is quite fast. The current in each of these branches is the same, but notice that on this portion right here, we're moving at 4 amperes. This portion all the way up here through branch 3, and then before this merge point is all 2 amperes. Here we have 4 amperes, and then when we get back towards the battery of 6 amperes. Hope that makes sense. So let's open these switches again, and let's make another change. And then now let's make resistor 2 12 ohms. This, I think, is what we did with series, except we just did 2 resistors, but again, it was series as opposed to parallel. Well, let's consider what's going to happen. First of all, the overall resistance needs to be less than 6 ohms. That's because via the reciprocal rule, the overall resistance is smaller than the smallest resistance. So 1 over 6 plus 1 over 12, and then reciprocate at the end, is 2 over 12 plus 1 over 12, which is 3 over 12. Reciprocate 12 over 3 is 4 ohms. 4 ohms is less than 6 or 12 ohms. Notice that that's going to be the overall resistance when both of these switches are closed. Next, notice that we can predict the current in each of these branches. We have to have 12 volts across each branch. 12 volts divided by 6 ohms, that's going to be 2 amperes. 12 volts divided by 12 ohms, that's going to be 1 ampere. So that's overall 3 amperes coming into or out of the battery. Now notice though, there's going to be twice as much current on branch 1 as branch 2. So more current, this is important, will follow the path of least resistance. You've probably heard this phrase before in your life, but you maybe didn't know what it was in context to. A good context to use that phrase properly is that in parallel circuits, we note that more current, not all of the current, but more current will follow the path of least resistance. There will be twice as much current in branch 1 than branch 2 because there's half the resistance. So let's close these switches. Notice that this bulb is going to be what? Well, it's going to be twice as bright as this bulb because it has twice the current. They both have the same they have different resistances. And let's see if we can calculate what the brightness is. So the brightness should be 12 squared, that's 144. In this case, divided by 12, so that should be 12 watts. But in this case, divided by 6, that should be 24 watts. So that's twice as bright. Notice the current going back to the battery is 3 amperes. That's because at this point, the electrons merge, and at this point they split up. Now, if you watch carefully here, you have to watch closely, that there's 2 electrons that enter this junction point from branch 1 for every 1 electron that enters from branch 2. And we send 2 electrons towards the middle branch, or that is branch 1, from this junction point, and then 1 goes up to the top. So this is what we mean by a parallel circuit with differing amounts of resistance. Notice if we were to close the other switch, we should send the same amount of current to this resistor. So let's do that. Notice these should be equal brightness. 2 amperes to the current, 5 amperes out of the battery, and then 1 ampere through this middle branch, branch 2. Okay, let us open all of the switches, not the switch by the battery. Finally, what if we had what we did a few minutes ago, where we kept this at 6. Let's have this go down to 2 ohms, and let's have this go down to 1 ohm. Now the battery is really going to work hard here, very hard, because the overall resistance is going to be smaller than the smallest one, so smaller than 1 ohm. And if you have smaller than 1 ohm, then there's going to be more than 12 amperes of current moving. Let's see if we can calculate. This is going to be 1 over 6 plus 1 over 2 plus 1 over 1, and then reciprocate at the end. So that's 1 over 6 plus 3 over 6 plus 6 over 6. So 1 plus 3 is 4, plus 6 is 10. You should get 10 over 6, reciprocate that, that's 6/10 or 3/5 of an ohm. So 3/5 of an ohm, that's the same thing as 0.6 ohms. 12 volts divided by, let's see, 12 volts divided by 0.6, 12 divided by 0.6, that should be 20 amperes. That's a lot of current that's going to be running. In fact, this might actually cause a fire, but let's see. And the simulation might not be able to handle it. It might be a little too fast. So let's close each of these one at a time. Notice, look at that. That's 12 amperes just on this branch. Let's go ahead and leave that off for now. Let's close the 6 ohm. Okay, so 2 amperes. Let's close the 2 ohm. Notice we have 2 amperes plus 6 amperes. That's 8 amperes into or out of the battery. That's because we know the current in each branch, branch 2 and branch 3, is given by Ohm's law. So that's going to be 12 volts for each branch divided by either 6 ohms or 2 ohms. So it's going to be either 2 amperes or 6 amperes. Then we should have 12 amperes for this branch right here. Now it would give us 20 amperes. Let's see what happens when we close this switch. Okay, we reached our limit and we actually have a fire. Now notice that's bad. So let's open this switch before something bad happens. Now by the way, in your household circuits, I mentioned before that devices are hooked up in parallel. But most household circuits have fuses. Now a fuse is an old school device. Nowadays it's an electronic breaker. And a breaker makes sure that a circuit is not overloaded with current, that is. Most circuits are rated for somewhere between 5 and 20 amperes. If it got larger than that, the circuit would get too hot and it could melt or even start a fire. And generally that's bad. So what we do is we make sure we put in those fuses or breakers in case that current is reached, and then it shuts off the circuit to prevent damage. So for safety. So household circuits need breakers or fuses for electric safety to prevent too much current from running. Okay. So, by the way, just for confirmation, let me see if I can show what the voltage is across each of these devices. So across this device, it should be, let's see here. So it's 0 volts because no current is running. Across this device, it should hopefully be 12 volts, and it is. It's also 12 volts across this bulb, and it should be 12 volts coming out of the battery. Okay, so that's what we should see. Okay, so it looks good. So I think that concludes this video on series and parallel circuits. Thank you very much for your attention. Please subscribe to the channel if you enjoy this content. Please share this content with people you know that would benefit from it. Please smash that like button if you like what you see, and I will see you in the next video. Thank you for your attention.